Have you ever tried teaching a dog a new trick, like sit or stay?
Oh, yeah. Patience is key. And lots of treats.
Exactly. Treats, praise, maybe a gentle no. It's
Yeah.
all trial and error, right? They try something, they get feedback, positive or negative, and slowly they figure it out.
Mm-hmm.
Well, that same idea, learning from rewards and consequences, that's actually how some really powerful AI learns. It's called reinforcement learning.
That's right.
And today we're doing a deep dive into exactly that, how it works, where it's had these really amazing successes, but also where the big challenges are, especially for real world stuff.
Yeah, and it's important to grasp that reinforcement learning, or RL, is quite different from other ways AI learns,
Mhm.
like supervised learning. That needs tons of labeled data.
Right, like showing it a million pictures labeled cat.
Exactly.
Ah.
RL doesn't get that. It's more like the dog analogy it learns
Mhm.
by interacting with its environment and seeing what happens. Getting that distinction is really key to understanding what AI can and frankly can't do right now.
Okay, so it's learning by doing, not by studying labeled examples. Can you break that down a bit more? What are the core pieces of RL?
Sure. Think of it like this. You've got an agent. That's our AI.
Okay,
And it's operating in an environment, which is often, a simulation like a game or a virtual world.
got it. Agent in an environment.
And the agent can take actions. Based on the action it takes in a particular situation or state, the environment gives it back feedback, but only in the form of a reward or maybe a punishment like a score.
So that reward signal is the only thing it learns from. It's not told, good job, you move forward, just plus 1 point.
Precisely.
Right.
It has to figure out which actions led to that reward. It's not explicitly told what the right move was. It discovers it through trial and error based entirely on that feedback signal.
And is the goal just to get the immediate reward, like the quickest treat?
Ah, good question. No, not necessarily. The real goal is usually to maximize the total reward over the long run. It has to learn a strategy, or what we call a policy, that leads to the best cumulative score over time.
So, like learning patience, don't just grab the first small reward if waiting leads to a bigger one later.
Exactly. It's about figuring out the sequence of actions that leads to the best overall outcome, even if some steps don't give an immediate reward. Think chess sacrificing a piece now for checkmate later.
Okay, that makes sense. Let's make it really concrete. You mentioned simulations. How about Rosie the robot dog learning to kick a soccer ball?
The perfect example.
So Rosie starts out just flailing around, right?
Uh,
Totally random movements, bumping into things.
Pretty much. Initially, it's just random exploration. She's trying things out.
Right.
Now, to keep track of what works, the AI might use something called a Q table.
A Q table? What's that? Like a scorecard?
Sort of, yeah. Think of it as a big cheat sheet or a table. It has rows for all the possible situations or states Rosie could be
Or
in.
like how far she is from the ball.
Exactly.
Yeah.
10 steps away, 5 steps away, 1 step away, right next to it, those are states. And the columns are the possible actions she can take. Move forward, turn left, kick, whatever.
Okay, states and actions in a table.
And each cell in that table holds a value, the Q value, which is the AI's estimate of how good it is to take that specific action when in that specific state. Initially, maybe all the values are 0.
Because she knows nothing yet.
Right. But then, maybe purely by chance, Rosie is 1 step away from the ball and she takes the action forward. Now she's 0 steps away. Then she tries kick, and let's say kicking the ball gives a big reward, like plus 10 points.
Uh-huh. Success.
Right. And that plus 10 reward is crucial. That information gets used to update the Q table. This is where backpropagation comes in, though it's a bit different in RL than in neural networks.
Backpropagation. Okay. How does that work here? How does that plus 10 for kicking help her learn that moving forward was also good?
Great question. It's not just the kick action's value that gets updated. The system looks back at the action that led to that successful state. So the value for taking forward when she was 1 step away also gets increased. Maybe it goes from 0 up to, say, 8.
Ah, I see. So it's like, hey, that forward move put me in position where I could get a big reward. So that move is probably pretty good too.
Exactly. It's learning the value of actions based on the future rewards they might lead to. The folks who developed this call it learning a guess from a better guess. The AI constantly refines its estimates in the Q table based on the rewards it actually receives. It learns sequences.
Learning a guess from a better guess. I like that. It really captures the trial and error refinement. And this whole process, it seems like it's worked incredibly well in games.
Oh, absolutely. Games have been the perfect sandbox for RL. You have clear rules, defined states, actions, and measurable scores, perfect for this kind of learning. AI pioneers like Alan Turing and Claude Shannon were thinking about game-playing AI way back, even before they had computers powerful enough to really do it.
Right, the fascination was there early on. And fast forward to today, DeepMind's AlphaGo. That was huge. It beat the World Go champion, Lee Sedol. How did it learn? Was it using this Q-learning approach?
It used a sophisticated version, yes, involving deep neural networks instead of just a simple table, often called deep Q learning or similar policy gradient methods. But the core idea was RL. AlphaGo learned primarily by playing against itself. Millions and millions of games.
Millions, just against itself.
About 5 million, yeah. It generated its own experience, figured out what worked, what didn't, and updated its internal neural network's parameters based on winning or losing those simulated games.
Wow. And then they took it even further with AlphaZero, right? That learned multiple games.
That's right. AlphaZero was even more general. It mastered chess, shogi, and Go. And the really mind-blowing part, it did it without human knowledge.
And you mean what exactly? No opening books, no expert strategies fed in?
Even more fundamental than that, it wasn't told the rules explicitly, or what a pawn or a king is, or even concepts like capture. In some versions, it learned just by looking at the pixels on the screen like a video game and playing itself. It figured out the optimal strategies completely from scratch.
Just from pixels and the score. Becoming superhuman. That's incredible. It really underlines what Demis Hassabis at DeepMind said, that games are just our training domain.
Exactly. The goal isn't just to win games. It's to develop these powerful general learning algorithms that can then hopefully be applied to messy, real-world problems.
Yeah, but that's the million-dollar question, isn't it? How well does it apply to the real world? Because the real world isn't a perfectly defined board game.
That's the major hurdle. And there are a few big reasons why it's so challenging. First, remember that Q table we talked about with Rosie?
Yeah, the state action cheat sheet.
Well, imagine trying to make one for a self-driving car. The number of possible states, based on sensor readings, GPS, weather, traffic, it's practically infinite. You can't make a table that big.
Okay, so the table idea doesn't scale. What do they use instead?
They use deep neural networks like AlphaGo did. These networks are good at generalizing, at grouping similar states together. So instead of needing an entry for every exact situation, it learns a function that estimates the value. But it's still incredibly complex.
And then there's the environment itself. Games are simulated, controlled. The real world, not so much. Is that the simulation gap people talk about?
Precisely. RL shines brightest in simulations, where you can run millions of trials safely and quickly, reset easily, and the rules are perfectly known. The real world is, well, real. It's messy, unpredictable. You can't just hit reset after a crash, and getting clear reward signals is often difficult. Think about teaching an AI to have a good conversation. What's the reward signal for that? It's very fuzzy.
Right. And does this lead to brittleness? Like the AI learns something very specific to the simulation, but it doesn't hold up if things change slightly.
That's a huge issue. We see what's sometimes called superficiality in RL solutions. There was a famous example with an AI learning the game Breakout. It got superhuman scores. But if you shifted the paddle just a few pixels up or down from where it learned, its performance completely collapsed.
Wow. So it hadn't really learned hit the ball with the paddle, but something much more specific about pixel patterns in that exact spot.
Kind of, yes. It learned correlations that worked incredibly well in that specific setup. Similarly, AlphaGo, for all its genius, couldn't play Go on a slightly smaller board or a differently shaped board without significant retraining. It didn't generalize the concept of Go strategy in a human-like way.
That suggests these systems, as amazing as they are missing something pretty fundamental about, well, intelligence as we know it, maybe abstraction or common sense.
That's the core of the critique from people like Gary Marcus or Oren Etzioni. They argue that deep learning and pure RL, on their own, might be hitting a wall when it comes to achieving genuine understanding or common sense. Humans learn concepts much more robustly from far less data.
We generalize incredibly well.
We do. And Marcus and others suggest that maybe we need more than just learning patterns from data. They believe common sense isn't just going to magically emerge from current methods alone. The focus for some is shifting towards things like unsupervised or self-supervised learning.
Learning without explicit rewards or labels, like how a baby just watches the world.
Exactly. Learning the background structure of the world, how things generally work, just through observation and interaction, before you try to achieve specific goals with RL. That might be the key to building that foundation of common sense that current systems lack.
So where does this leave us with the big dream of artificial general intelligence, AGI? Is RL the path or just part of the path? I remember Fei Li describing AGI as needing to be contextualized, situationally aware, nuanced. That sounds like more than just maximizing a reward signal.
I think most experts would agree RL is a crucial tool, a very powerful piece of the puzzle, but probably not the whole picture for AGI. Fei Lei also mentioned needing unsupervised learning, virtual learning, many kinds of learning.
So combining approaches?
Very likely. Continued progress towards more human-like AI will probably require integrating RL with ideas from other areas, maybe explicit ways to handle symbols, logic, hierarchical understanding of language and the world, things that current deep RL struggles with. We're still, realistically, quite a long way away from that kind of flexible, human-level AGI.
Okay, so let's wrap this up. Reinforcement learning. It's this powerful idea, like training a dog, where AI learns through trial and error, chasing rewards over the long term, learning by doing. And it's led to absolutely stunning results in controlled environments like games, AlphaGo, AlphaZero, superhuman performance learned from scratch.
Incredible feats in those domains, yes.
But, and it's a big but, there's this gap between the clean world of simulations and the messy, unpredictable real world. Scaling issues, the simulation gap, the superficiality where the learning doesn't always generalize.
Right, the common sense problem looms large.
It seems like getting to truly intelligent, adaptable AI might require more than just pure RL, maybe blending it with other techniques like unsupervised learning to build that deeper world understanding first.
That seems to be the emerging consensus. RL is a key component, but perhaps not sufficient on its own for the AGI mountain peak.
Which leaves us with a pretty interesting thought, doesn't it? When you think about how we learn kids especially, so much of it is just watching, playing randomly, not always trying to achieve a specific goal or get a reward.
Exactly. Observation, curiosity, unsupervised exploration seem fundamental to human learning.
So what's the AI equivalent of that? What kind of, I don't know, underlying structure or learning process does AI need to truly bridge that gap from mastering specific tasks to having general adaptable intelligence like ours? That feels like the next frontier.
It really does. How do we build systems that learn the fabric of reality itself, not just the rules of the current game? That's a profound challenge.